Another metric that often has to be considered is mean square error. Now, mean square error is used more in contexts where the data is continuous. That is, we just have far too many possible labels. Now, in actuality, the data might not be truly continuous in the precise mathematical sense. However, the point is there's just far too many labels to really construct a Confucian table. Now, what's an example of this? We could have, for instance, if we're predicting some sort of dollar amount, prices can range quite drastically. But not just that, there's also different levels of precision. We may be going down to the cent, right? We could have $1,000.51. We could have $1,000.52, $1,000.53, and so on and so on. There's just so many possible labels that we have that we need a different metric. Let's say y represents the actual label of one of the data points in our testing set. So y at I is going to be the actual label for the ith data point. So y1 is going to be the label for our first data point, and we'll say that is 2.0. And y2, which is the actual label for our second data point, is 5.5. So those are actual labels for our two data points in our testing set here. A very small testing set. Now, y hat at I is going to be the prediction that our model makes for that data point given its feature vector. So let's see. For the first data point, it predicted a 4, which of course is off by 2. For our second data point, our model predicted a 3.5. Now, we can determine how much our model was off and the error for each data point by just subtracting those two values. Right? So for the first data point, if we subtract 2 from 4, we get -2, meaning that our prediction should have been 2 lower. Okay, if we do this for the second data point, we get 2, meaning our prediction should have been 2 higher. So these values can represent our errors. But if we want the overall error for our model, given this testing set, which only has 2 data points, I guess we would just add these errors. So we would add -2 to 2. But the problem here is that -2 plus 2 cancels out. It's 0, meaning our error would be 0. And that kind of seems odd because in both our data points, our model was off by 2, yet the error is now 0. One way of solving this that it's mathematically the best way to do it, is to square this error. So we take these two values we have and square them, and in both cases we happen to get 4. This gets rid of negatives, so there's no cancellation. If we add these now, our error is 8, which is a better representation of how off our model is than 0, because 0 means our model is perfect, if you think in terms of error. But 8 gets a pretty good sense of how off the predictions were. And this is called squared error. And the mathematical formula for squared error is this, where that Greek letter sigma means the sum. And we're just assuming we're taking the sum of these squared errors for all of our data points. In our case, we just had 2, and we got a squared error of 8. Though, of course, in practice, you'll have much larger testing sets. And so you'll be taking the sum of the squared errors for far more data points. Now, the common thing to do from here, once you've calculated the square error, is to find the average square error, or the mean square error. And that kind of tells you approximately how much error we have for each prediction. So we divide our error amongst how many data points we had in our testing set. So we divide by n. And we get the mean square error, which is 1 over n multiplied by our squared error, or the sum of our squared error. Another popular metric is the root mean square error, which is simply just the square root of our mean square error. And of course, the squared doesn't just cancel out, but it's an attempt to kind of make that cancellation, even though it's not perfect.